Greetings, my name is Professor Duke Orata. We are continuing with our lectures and we are still looking at steady flow, and we'll move on to jet propulsion and the likes as we coordinate, as we interface and coordinate whatever we have discussed. Now, we are still looking at matters at the throat of that particular duct, and so we want to calculate the velocity at the throat. We have discussed this in the previous lectures, and I continue urging and requesting you to go through all those lectures systematically so that we are all together. Now, you remember we had that expression in those previous lectures. We had the expression for velocity where we had 2n, 1 minus n, p1 v1 into p2 p1, n minus 1 over n minus 1. And of course, this is to the square root. So this was a fundamental expression which we had gotten. And we had also gotten that expression for critical pressure ratio at the throat, and for the critical pressure ratio that was P2 over P1 was 2 over n plus 1 into n over n minus 1. So I got those expressions 1 and 2 because we're going to use them in our derivation of the throat velocity. Now, we can remove the square root to make our life easy. So just removing the square root, we just will have c squared is equals to 2n over 1 minus n p1 v1 into p2 p1 n minus 1 over n minus 1 instead of being raised and the square root. We have removed the square root, so we just square both sides. And remember, n is still the asymptotic index of expansion, which we got in the polytropic equation. And I keep repeating for the perfect case that n is gamma, which is the ratio of the isobaric and isochoric heat capacities. And otherwise, for steam, for example, n will have a value of about 1.135, and in the superheat region, we'll have it at 1.3, and so forth and so forth. Those we have discussed those in the previous lectures, and it's very important for us to know that. Now, let's call this expression number 3. So if we substitute the expression 2 into 3, because you want to calculate the throat pressure, so if we substituting 2 into 3, we end up with a very simple expression. We are just substituting P2, P1 into that quantity expression there, P2, P1. So that will be c squared will be 2n over 1 minus n p1 v1 into 2 over n plus 1 raised to n over n minus 1, and of course raised again to n minus 1 over n minus 1. So we have just put the expression for the critical pressure ratio there in this particular expression there, and it was raised to n minus 1, and of course it's still raised to n minus 1, n minus 1. And we are still using that identity which we talked about last time. So if you have x to the y raised to power m, that is the same as x y times m. So that's the identity which we'll apply here to simplify our index there. So using that particular identity, so using this identity here, we will simplify this expression there. Therefore, c squared is equals to 2n over 1 minus n p1 v1 into 2 over n plus 1 into n over n minus 1 times n minus 1 over n minus 1. And of course, those cancel, so it's raised to power 1. So we have c squared is equals to 2n 1 minus n p1 v1 into 2 over n plus 1 minus 1. So let's call that expression 4. So we just simplified the exponents using that identity there. Now, remember, we say that for the polytropic equation, from polytropic equation, P1, V1 per n is P2, Pt, Vt per n. And so, we can simplify these exponents. We can simplify these exponents. In this particular case, we can simplify these exponents here and realize that Pt, Vt is simply equals to P1, V1. And so in place of P1, V1, we can have Pt, Vt based on that polytropic expression there. So let's work with that one now. So from polytropic equation, so C2, therefore C2 squared is 2n over 1 minus n into Pt, Vt into 2 over n plus 1 minus 1. And so we are making progress. We are making a lot of progress. Now, the second realization, which we had already identified in the previous lectures, was that, also note, that 2n over 1 minus n can be written as, if we write it as minus 2n, 1 minus n, write that now as 2n over n plus 1. And so using that in place here, so we can have c squared is equals to 2n over n plus 1 pt vt into 2 over n plus 1 minus 1. So our life is becoming simpler. You already see there's 2 over n plus 1 here, so we can multiply it in this particular bracket here. Therefore, c squared is equals to n pt vt into 2 over n plus 1, 2 over n plus 1 times 2 over n plus 1 minus 2 over n plus 1. Very simple. Just open up the brackets, multiply 2 over n plus 1 multiplied by 2 over n plus 1 times minus 2 over n plus 1. My life is becoming a lot easier now. We are reducing it easily now because now there are many like terms. And so what do we have here? So we have c squared is equals to n pt vt into 2 over n plus 1 squared minus 2 over n plus 1. We can simplify this by dividing that. So dividing the bracket by 2 over n plus 1. To simplify it, you have c squared. Just dividing by 2 over n plus 1 will be n pt vt into 2 over n plus 1 squared divided by 2 over n plus 1 minus 1. And of course, that is very simple. That will be n pt vt, as I've written a little bit high up, n pt vt into 2 over n plus 1 minus 1. So if you open up that quantity there, so we'll have c squared will be n pt vt into bracket n plus 1, 2 minus n plus 1, and of course that quantity there, this particular quantity here, will be 1, and so what do we have here? We will have this quantity as 1, so that will be c squared. That will be c squared is equals to n pt vt. So that quantity will have reduced to 1. So, in a nutshell, the velocity at the throat is given by the expression c, because now, because that's c squared, take the square root, will be n pt vt, the square root. And that will be the throat velocity. And you're clearly seeing that the isotropic index, we have our pressures, and we have our specific volume. And so if you go through our lectures, we have dealt significantly with all these quantities. We talked about the critical pressure ratio, that's the one you accelerate the fluid to the velocity of sound, and so forth. We talk about those transitions from subsonic to sonic. We have looked at them in the previous lectures, and I continue encouraging you that you look at all those lectures. So we'll stop at this point. We are still continuing with our lectures on steady flow and jet propulsion. Thank you.